Whether we live in a house that is 500 years old or one that is newly built, we all know that it is much more comfortable for us to be in a building that is dry and well maintained. Some buildings are notoriously difficult to keep weatherproof. For instance, badly designed flat roofs may have insufficient fall to shed rainwater. Guttering may become blocked through neglected maintenance, causing the hopper head to overflow, which results in water penetrating the fabric of the building. This penetration will be all the more rapid where defects such as cracks in the rendering have been allowed to occur. Alternatively, where the damp-proof course is non-existent or has become damaged, rising damp may develop. Condensation may occur where relative humidity is high and insulation, ventilation and heating are poor or non-existent. As well as creating unhealthy conditions for the occupants of the building, these three causes of excessive dampness can result in the building fabric itself deteriorating, as can be seen here where the rendering is cracking and flaking off, and where the mortar pointing has become porous, allowing brickwork to decay. Another frequent feature of dampness is the development of mould growth, especially on internal cold wall surfaces in corners of rooms. Dampness can lead to high timber moisture content and the development of decay, such as wet rot or dry rot. Other consequences of dampness are spoilt decorations or even detached wallpaper, and the deposition of moisture-attracting mineral salts, such as sodium chloride, which contributes to plaster deterioration. Penetrating dampness almost always occurs as the consequence of defects in the building envelope. Perhaps a slate, for instance, has slipped, allowing rain to penetrate. On this chimney, we can see the flaunching is deteriorating and the mortar pointing between the stones is being weathered away. Here, the gutter and downpipe are disconnected. The gutter end is not properly supported and an overflow will occur. Cracks in the cast iron rainwater downpipe and the blocked hopper head will deflect water onto and ultimately into the wall. Damp brickwork is more likely to be damaged by frost, which causes the bricks to crumble. Once detected, these causes of penetrating damp can usually be repaired by conventional building techniques. As its name suggests, rising damp originates in the ground, from where there is a constant upward movement through any porous material. The tiny cracks that are normally present in masonry, mortar, brick and stone provide the pathways for this ascent. In the laboratory, we can illustrate this phenomena by inserting tubes of varying diameter into coloured water, and it can be seen that the water rises highest in the narrowest tube. This movement is called capillarity. In a 225mm, that is, a 9-inch solid wall, rising damp would be expected to rise to about 1 metre or about 3 feet above ground level. At this height, the evaporation rate off the wall exceeds the supply of water rising from the ground below by capillarity. If the drying out of the wall is restricted by an impervious rendering or a matchboarding dado, for example, the moisture may be forced even further up the wall. An abutting wall without a DPC can produce a similar effect. Rising damp may also reach a greater height in a thick wall as the area of contact of the wall base with the ground is greater and the evaporating surface is less as a proportion of the total wall volume. As the moisture rises from the ground, it carries dissolved mineral salts which are naturally present in soil water. As the water evaporates off the wall, these salts are deposited, and on brickwork they are often visible as a white deposit, which is called efflorescence. On a plastered wall, these salts, which are mainly chlorides and nitrates, cause damp and discoloured patches to develop, and ultimately complete disintegration of the plaster. As the rising damp moisture flows through the masonry, the amount of moisture declines the further it gets from the source, and as the water content declines, the accumulation of mineral salts increases. Under conditions of high humidity, at 80% relative humidity for example, these salts attract water vapour to themselves, and as a result considerably swell in size. This is called hygroscopicity. Sodium chloride is a hygroscopic salt. In many situations, some salts, such as calcium chloride, can attract so much water that they turn into a liquid. These salts are known as deliquescent salts. Whenever rising damp occurs, the total moisture content is made up of two components. Hygroscopic moisture is introduced as a result of the absorption of atmospheric water vapour by the salts present in the wall. The second component is moisture that has risen from the ground by capillarity. This is the major component at the base of the wall, and the hygroscopic moisture is predominant higher up. So in every case of rising damp, these two components have to be recognised and remedied. Rising damp moisture from the ground characteristically contains nitrate and chloride salts, and high percentages, 9.5% to 16%, can be found on wallpaper when rising damp has persisted for a long time. The presence of these salts can be confirmed chemically using special test papers which are decolorized by chlorides, and this test is a sure sign of rising damp. Rising damp is normally prevented by the insertion of a physical damp-proof course during the construction of a wall. These DPCs may deteriorate with age or be made ineffective by external bridging with a cement plinth, for example, or by external rendering being applied right down to ground level, or by concrete slab foundations as used for oil storage tanks, enabling moisture to bypass the DPC in the wall. Another all too common example of bridging is caused by high soil levels of flower beds. Internally, a floor screed can cause bridging if its membrane does not key in and become continuous with the DPC. Plaster can also bridge internally when applied to the base of the wall and in contact with the floor screed. Mortar droppings in a cavity wall can also make a DPC ineffective by allowing the moisture to bypass it. Condensation is a common occurrence in buildings today. It is caused by reduced ventilation, lower heating levels, and poor insulation. When humid air condenses water vapour on cold surfaces, water droplets form. Very often it is the activities of people in buildings that cause high humidities. Portable gas heaters which have no flue for venting the vapour can produce just as much. It is amazing how much water vapour is produced by everyday events. A family of 4, just breathing, can produce up to 4 litres of water per day. Cooking can produce 2 litres per day. The washing and drying of clothes can produce up to 8 litres per day. And, of course, showers and baths are additional sources of water vapour. Most of the time we are not aware of the presence of this vapour in the atmosphere, but if the temperature falls or if warm, humid air penetrates into cooler areas, condensation will occur on the colder surfaces. This can lead to the growth of mould, which develops on surfaces where condensation is occurring. Typically, mould growth is found on the north and east corners of poorly heated, badly ventilated and uninsulated properties. Mould growth can also occur on timber in pitched roofs where the roof void is not ventilated, or where ease ventilation has been obstructed by insulation. So, to sum up, we have seen how excessive dampness can be caused by water penetrating or rising into the building, or by condensation. The correct diagnosis of these problems is essential before the appropriate remedial measures can be specified. A survey of a building will involve a visual inspection of building defects and their effects. The moisture meter is a most valuable instrument in that it can measure the conductivity of a section of wall between the needles of the probe and can be used to establish moisture patterns which help to locate the source of dampness and characterize it. In this situation, on a solid 9-inch external wall, meter readings confirm penetrating damp from around the window and also show the effect of water splash-up from an overflowing system at first floor level. In this example, on a cavity wall, wall ties are bridged with mortar, and this is causing damp to penetrate. Lower down the wall, mortar droppings bridge the DPC and rising damp is developing. Meter readings should be interpreted after due consideration of the building defects and their effects. There is a great temptation to classify everything as rising damp when often it isn't anything of the sort. For instance, here we see overflowing gutters causing water splashback and penetration through a solid wall above DPC level. And here, water penetration is a result of inadequate throating and projection of the windowsill. Each of these defects might be diagnosed as rising damp at first sight, rather than the penetrating damp it really is. In a room, humid air can be cooled by proximity to a cold exterior wall down to a temperature where condensation develops in a manner resembling rising damp. Fortunately, there are several clues to making the correct diagnosis. Moisture meters show low readings with condensation and high readings with rising damp due to the presence of salts which increase conductivity. When a meter reading is taken at the top level of the dampness, a gradual change is typical of condensation and a sharp change with rising damp. Mold growth is more typical of condensation, and the pattern of growth can be a helpful confirmatory feature. Hygroscopic salts are absent where condensation alone is the cause, but their presence is diagnostic in cases of rising damp, where the presence of nitrates and chlorides can be confirmed by chemical laboratory tests. But when all is said and done, it's the careful observation of defects, a sound knowledge of the effects of dampness, the intelligent use of the moisture meter, and a detailed knowledge of the characteristics of rising damp which are essential for correct diagnosis. In the next program, we shall look at the correct remedial measures for eradication of rising damp.